Hi, today we're going to have a look at Euler's formula. Euler's formula is another nice looking formula in complex numbers which allows us to quickly and simply write things that are in modulus argument form. It's less writing and it allows us to quickly calculate things. Now, a lot of people think that going from modulus argument form to Euler's formula is kind of just something that we defined randomly to be true, which is actually false. We can use something known as a Fourier series and a Maclaurin series, different applications of that, which is quite high order university mathematics. And if you do that, you actually end up getting that this is the same as that. So we're going to say that r, outside of cos theta plus I sine theta, is equal to r e to the I theta. So note that the rules for the multiplication and division of complex numbers in mod arg form, as well as de Moivre's theorem, still applies to Euler's formula. So I might do just example A and B for this video. The rest we'll do in class. We're going to write each complex number in both polar and Cartesian form. Now, polar form is another way of saying modulus argument form, and Cartesian form, of course, is written with our square roots and our I. All we have to do to go into polar form is look at the coefficient of our e, which is 1. So the modulus of this complex number is 1, and it's just cos of pi on 6 plus I sine of pi on 6. And then going now to Cartesian form, cos of pi on 6 is root 3 on 2. Sine of pi on 6 has to be 1. So the answer is that this is root 3 on 2 plus I times by a half, or we could say root 3 on 2 plus I on 2. Okay, part B, again, the coefficient of e is 1, so the modulus of this complex number is also 1. So this is cos of negative pi on 3 plus I sine of negative pi on 3. Now, something nice about complex numbers that we're going to start to get used to is the fact that this is actually the same as cos of pi on 3 minus I sine of pi on 3. Now, a lot of students just like to memorize and know that that's true, but the actual reason is because cos of negative theta is the same as cos of theta, and sine of negative theta is the same as negative sine of theta. Now, cos of pi on 3 is 1 on 2, and sine of pi on 3 is root 3 on 2. We get root 3 on 2i. And those are those two done there. So, of course, we can go back the other way. So we can go from, I might do A and B. We can go from our Cartesian form into Euler's formula. So the first thing we need to do is figure out our theta, and theta, which is our argument, is tan inverse of y on x, which is tan inverse of 2 on 2, which is 1, and tan inverse of 1 is, oh no, sorry, I'm a bit dumb here. I'm thinking it more as a vector, little extension 1 auxiliary angle method, not quite. We're actually told, I'm sorry, that the angle just in here is 2, so 2 radians, and we can just say it's 3 e to the 2i. It's a really weird way of doing that, saying the angle is 2. It just means 2 radians. It stumped me there. But yeah, we're just going to say e to the 2i, so that angle inside there is 2. We do part B. It's always best to draw a little diagram. The real component is 1, but it's going in the negative direction, and the imaginary component is root 3. And we figure that out. Tan inverse of 1 on root 3 is pi on 3, but we want the principal argument, which is that angle there, which is going to be pi minus pi on 3, which is 2 pi on 3. So this one is, we've figured out the argument is 2 pi on 3, and the modulus, well, the mod of z mod z is equal to the square root of 1 plus root 3 squared, or 1 squared plus root 3 squared, which we know is 2. So this complex number from part B is the same as saying 1 plus I root 3 is the same as 2e to the I 2 pi on 3. We'll do one more example and then we'll conclude the video, just to reinforce the fact that De Moivre's theorem still applies for Euler's formula. I'm going to have a go for De Moivre's theorem at part C. So given that z1 is 2i to the pi on 6, z2 is 3e to the minus pi on 3, and z3 is 3i to the pi on 4, find the polar form for each of the following. Remember, polar form is another way of saying modulus argument form. So z1 squared is 2e to the I pi on 6 squared. Remember, to square a complex number, we use De Moivre's theorem. 2 squared is 4. E to the I. Pi on 6 times 2 is pi on 3. And we have to then multiply that by z2, which is 3 e to the minus I pi on 3. Now, 4 times 3 is 12, and when we multiply indices, we add the powers. So pi on 3 plus minus pi on 3, we get 0. So it's e to the I times 0. Anything to the power of 0 is 1, so the answer is 12. So just to recap what we've done, we've said z1, we wanted to find z1 squared, so we've applied De Moivre's theorem. We've gone 2 squared is 4, and then pi on 6 times 2, which is what De Moivre's theorem tells us to do, is pi on 3. And it then told us to times by z2, which is 3e to the minus pi on 3. But again, when we multiply complex numbers, or the same as multiplying indices, we add the powers. And if we do that, we get 0. Pi on 3 minus pi on 3 is 0. So I is 0, and anything to the power of 0 is 1. So the answer is 12. So that in a nutshell is Euler's formula. Of course, in class, we will get into some harder examples, but this is just an overview of Euler's formula.